In 1947, a newly born nation inherited a death sentence. Pakistan's farmland was withering, its rivers were being diverted, and 100 million people were about to face the world's largest water crisis. The Indian subcontinent had just been carved in two, and the border didn't just divide people, it divided water. Within months, India shut off the canals feeding Pakistan's Punjab, the breadbasket that fed the entire nation. Crops died in the fields. Farmers abandoned their land. Famine loomed. But what happened next would become the largest irrigation project ever constructed by human hands. A system so vast it would reshape the geography of an entire country and turn bone-dry desert into an agricultural powerhouse. This is the story of the Indus Basin irrigation system. The crisis. To understand the scale of what Pakistan built, you first need to understand what it was up against. The partition of India in 1947 created more than just political borders. It created a hydrological nightmare. The Indus River and its 5 major tributaries, the Jhelum, Chenab, Ravi, Beas, and Sutlej, had sustained agriculture in the region for over 5,000 years. Ancient civilizations had thrived here precisely because of this water. But when the border was drawn, it cut straight through the irrigation canals that fed millions of acres of farmland. Pakistan controlled the lower basin. India controlled the upper reaches and the headworks, the crucial infrastructure where water is diverted from rivers into canal systems. On April 1st, 1948, less than a year after partition, India exercised its new power. It shut off the water supply to Pakistani canals. The message was clear: control the water, control the nation. The immediate impact was catastrophic. Pakistan's Punjab province, which produced 75% of the country's food, began to dry up. 10 million acres of irrigated land were under threat. The region that had earned the name Land of 5 Rivers was about to become a dust bowl. Pakistan had 2 choices: accept dependence on its rival for its most basic resource, or build something unprecedented. The solution takes shape. The engineering challenge was staggering. Pakistan needed to create an entirely new water distribution system that could bypass Indian-controlled infrastructure and deliver water across hundreds of miles to millions of acres of farmland. This wasn't just about digging a few canals. It required reimagining how water could be moved across an entire country. In 1960, after years of tense negotiations, the World Bank brokered the Indus Waters Treaty between India and Pakistan. The treaty gave Pakistan exclusive rights to the western rivers, the Indus, Jhelum, and Chenab, while India received the eastern rivers. But there was a massive problem. The western rivers didn't flow where Pakistan's farmland was. The eastern rivers did. Pakistan's agricultural heartland in Punjab depended on water from rivers that now belonged entirely to India. The solution was audacious: build a system of massive link canals that would transfer water from the western rivers across the country to the eastern farmlands. It would be the largest interbasin water transfer project in human history. The World Bank assembled the funding, over $1.3 billion, equivalent to roughly $13 billion today. Pakistan assembled the engineers, the workers, and the will to build it. Construction of a mega project. Construction began in the early 1960s, and the numbers are almost incomprehensible. The Indus Basin project wasn't a single structure. It was an entire ecosystem of engineered waterways. At its heart were 2 enormous link canals that would become the arteries of Pakistan's agricultural system. The Chashma Jhelum Link Canal stretches 211 miles, transferring water from the Indus River to the Jhelum River. The Taunsa Panjshad Link Canal runs 177 miles, connecting the Indus to the Sutlej River system. These weren't small channels. They were massive concrete rivers, some sections over 200 feet wide and 20 feet deep, carrying enough water to fill an Olympic swimming pool every 3 seconds. But link canals were only the beginning. The system required 8 new dams and barrages to control river flow and direct water into the canal networks. The Mangla Dam, completed in 1967, created one of the world's largest reservoirs, over 97 square miles of water storage capacity. The Tarbela Dam, finished in 1976, became the largest earth-filled dam on the planet, requiring 138 million cubic yards of earth and rock. For perspective, That's enough material to build a wall 3 feet thick and 6 feet high from New York to Los Angeles and back again. The canal network itself expanded to over 40,000 miles of channels, enough to circle the Earth nearly twice. Every mile had to be precisely graded to ensure water flowed at the correct speed. Too fast and the canals would erode. Too slow and silt would choke them. Engineers created a gravity-fed system that required no pumping. The entire network relies on the natural slope of the land and the elevation differences between rivers. Constructing this system required moving more earth than the Suez Canal and the Panama Canal combined. At peak construction, over 100,000 workers were employed. They worked through scorching summers where temperatures exceeded 120 degrees Fahrenheit, and through winters in the mountainous north where construction sites were blanketed in snow. Thousands of villages had to be relocated. Entire valleys were flooded to create reservoirs. Engineering challenges. The technical challenges went far beyond simple excavation. The Indus River system is one of the world's most sediment-laden rivers, carrying over 400 million tons of silt annually, more than the Nile or the Mississippi. This sediment is both blessing and curse. It enriches farmland with nutrients, but it also clogs canals, fills reservoirs, and damages infrastructure. Engineers designed sophisticated settling basins where water velocity decreases, causing sediment to drop out before entering the canal system. The major barrages feature gates that can be opened during floods to flush accumulated sediment downstream. But managing this silt remains an ongoing battle. The Tarbella Dam's reservoir has lost over 30% of its original capacity to sedimentation. Billions of tons of earth slowly filling what was once open water. Salinity presented another massive challenge. Irrigation without proper drainage causes water tables to rise, bringing dissolved salts to the surface. As water evaporates in Pakistan's hot climate, it leaves salt behind, poisoning the soil. By the 1960s, waterlogging and salinity were destroying over 100,000 acres of farmland every year. The solution required building one of the world's largest drainage systems, a mirror network beneath the irrigation canals, using tube wells and drainage channels to lower water tables and flush salts away. The system also had to account for Pakistan's extreme climate variability. The Indus system depends on glacial melt from the Himalayas and monsoon rains. River flow can vary by a factor of 10 between winter low flows and summer peaks. The dams and reservoirs serve as buffers, capturing floodwaters and releasing them during dry seasons. But even with massive storage capacity, balancing supply and demand across thousands of miles of canals requires constant adjustment, transformation, and impact. The results transformed Pakistan. Before the Indus Basin Project, Pakistan had 20 million acres of irrigated land, most of it under threat. Today, the system irrigates over 48 million acres, making it the largest contiguous irrigation system on Earth. Pakistan went from facing famine to becoming one of the world's top 10 agricultural producers. It's now the world's 5th largest producer of sugarcane, 6th largest producer of dates, 8th largest producer of wheat, and 10th largest producer of rice. The population that the system supports has grown from 40 million in 1960 to over 240 million today. Agriculture employs 40% of Pakistan's workforce and accounts for 19% of GDP. The water that flows through these canals quite literally sustains the nation's economy and feeds its people. Without the Indus Basin irrigation system, modern Pakistan as we know it could not exist. The system has also generated massive amounts of hydroelectric power. The Tarbella Dam alone produces over 3,500 megawatts, providing electricity to millions of homes. Combined with the Mangla Dam and other facilities, the Indus system generates nearly half of Pakistan's hydroelectric capacity. Ongoing challenges. But 6 decades after its construction, the system faces existential threats. Climate change is altering the Himalayan glaciers that feed the Indus River. These glaciers are melting faster than ever, causing short-term increases in river flow, but threatening long-term water security as ice reserves diminish. Scientists project that Indus River flows could decrease by up to 30% by the end of this century. The infrastructure itself is aging. Many barrages and canals are operating decades beyond their design life. Sedimentation continues to reduce reservoir capacity. Water losses through seepage and evaporation waste up to 40% of the water that enters the system. Pakistan needs billions of dollars for maintenance and modernization, but resources are scarce. Population growth and agricultural expansion have pushed the system beyond its original design capacity. Pakistan is now one of the world's most water-stressed countries, with per capita water availability dropping below 1,000 cubic meters per year, the internationally recognized threshold for water scarcity. Disputes between provinces over water allocation have intensified, and tensions with India over the Indus Waters Treaty periodically flare up. Yet despite these challenges, the Indus Basin irrigation system remains one of humanity's most impressive engineering achievements. It's a testament to what's possible when nations commit to infrastructure at a truly transformative scale. This system didn't just solve a crisis, it built a nation's future. The Indus Basin irrigation system proves that mega projects can change the fate of nations. If you found this story fascinating, hit that like button and subscribe for more deep dives into the world's most ambitious engineering projects. Drop a comment below. What mega projects should we explore next? Thanks for watching, and I'll see you in the next one.